This is our current paradigm for solving a linear system by Gaussian elimination. So if we're given a system AX equals B, we first factor A into L times U, and then we solve two triangular systems. We solve one with forward substitution, and then we solve another one with backward substitution using the U matrix. But we already know from simple examples that sometimes the process that we've described so far is going to fail. So as a simple example, here's a matrix A, a 2x2 example, where when we look at this matrix, right, the first thing we want to do is put a 0 here, okay, by adding a multiple of the first row. Well, the element that's above it is a 0, so no matter what multiplier we choose for the first row, we can't change the second row at all. So this number 0 here that's on the diagonal is called the pivot element. And if the pivot element is 0, Gaussian elimination cannot continue. Now, in this particular matrix, there's a very simple remedy, and probably one that you learned in your linear algebra class, which is that you're allowed to swap rows. So if we swap the two rows of that matrix, so for a 2x2 matrix, this little guy here, right, just swaps the rows of A. So the first row of the new matrix is the second row of A. The second row of the new matrix is the first row of A, and so that just swaps the two rows. And in that one, not only can you do Gaussian elimination, but you're done, because it's already upper triangular, and so the factorization is complete. So we know that we have to swap rows when we get a 0 pivot element. And so all we have to do is just look for a row down below. Right? We never want to change the rows above. That would destroy the zeros we've introduced. So we want to look for a row below the diagonal that has a non-zero pivot. But what's interesting and important is that sometimes we should swap rows even when the pivot is non-zero, but a small number. And small here is going to mean in absolute value. So let's go back to the instability lecture. So this is all copied from there. We had this problem of the intersection of two straight lines, one of which has a slope of exactly 45 degrees, and one of which has a very shallow slope. And remember, they intersect exactly at the point 1, 1, which is what we're trying to find for the solution. Well, when we solved for the first equation and substituted that into the second equation, then the numerical procedure we got returned the exact answers in floating point arithmetic. However, if we went the other way around, if we substituted first for the second equation, or solved first the second equation and substituted into the first, then y was okay, but x, right, had lost about 8 digits or so of accuracy. So if we look at this example in terms of factorization, we get another interpretation of what happened. So method 1, we can think of writing the first equation first, the second equation second, and then we just do Gaussian elimination, keeping track of the factors, and we get the following L times U for A. On the other hand, if we put the second equation first and the first equation second, we get two different factors, L and U. Now, in order to make L times U equal A, look at what happens when we compute the 2 element. So in this matrix product, if we take the inner product of that row with that column, we get minus epsilon inverse, that's a big negative number, right, plus 1 times epsilon inverse minus 1. Right? And that's supposed to come equal to negative 1, which is the value in this corner element. So mathematically that's correct. But numerically, right, what happens is that you have two very large numbers with opposite signs, right? These numbers are nearly equal, opposite signs, and they cancel to get a small result. Now, small in this case is negative 1, but compared to epsilon inverse, that's tiny. If epsilon was 10 to the minus 10, right, you're asking minus 10 to the minus 10 plus 10 to the minus 10 to approximately cancel out to negative 1. And so you're going to lose a number of significant digits in that subtractive cancellation. So when we factor the matrix according to method 2, we're relying on cancellation error to produce the matrix A. On the other hand, in method 1, that doesn't happen. So if we look at the same process for computing the 2 element of A, if you go through that, you'll see it does not rely on any particular subtractive cancellation of nearby numbers. And so that's a key difference between the two approaches. And really, a detailed analysis shows that the problem is whenever you have a pivot element which is smaller than the other elements in its column, this kind of thing can happen. And so what we end up with is a simple rule that we call the row pivoting rule, or sometimes it's called the partial pivoting rule. When we do elimination in column number K, okay, so we want to put zeros below the KK element, we look for the largest possible element in absolute value on row K and below, and we swap rows to put that into the pivot spot. So that might sound confusing, but in practice it's quite simple. So here's an example. Here's our same 4x4 matrix as we did for the PLU factorization. Now, in this case, we want to start with K equals 1. We want to put zeros in row 1, column 1, below the diagonal. Well, the largest pivot element, after taking an absolute value, is negative 4. So this should become the pivot. So that means we need to swap row 1 with row 2, which is exactly what this line does. Okay, so now we swap those two rows. The negative 4 is our pivot. Now we do standard Gaussian elimination step. Find the row multipliers, store them in L, and then apply them to a row operation, and we've done elimination in the first column. Now we want to do elimination in the second column. So K is equal to 2. So we look for the largest pivot element in row 2 and below, and that's the 16.25. So we want to swap rows 2 and 3. And that's what we do in this line. Do another standard Gaussian elimination step. The row operations, and A now has zeros in the first two columns. Finally, we're going to do the third column. So the largest possible pivot element is in the fourth row, so we have to do another swap. Do the Gaussian elimination, and we're done. So this is now our U matrix, upper triangular. Now, the details are a little bit complicated. There's a little bit more linear algebra to show what happens in terms of factorizing, because while this is U, it's not so clear what's happened to our L. Remember, our L before came from some lucky matrix multiplications working out just the way we wanted. Well, it turns out that we get lucky again, and we can express all of this in a very simple way, just by adding what's known as a permutation matrix. So permutation matrix is an identity matrix with reordered rows. And given that permutation matrix P, then the factorization becomes P times A is equal to LU. So if we now ask MATLAB to do this is a built-in LU, built-in function for doing row-pivoted factorization. MATLAB doesn't give you one without row pivoting because it's useless on matrices where we would divide by 0. So if you ask for 3 outputs from the LU function, you get the L, the U, and the P. Okay, so you see L is unit lower triangular. U is upper triangular. It's the same U that we got when we went through the process before. Okay, it's the same A that we ended up with before. Here's our U. And here's our permutation matrix P. So if we do P times A, right, that just reorders the rows of A. So the first row of the answer is the second row of A. The next is the third row of A. And we get the fourth row of A. And finally the first row of A. And that reordering is done in such a way that P times A is equal to L times U. We've checked. Now what does this mean for solving a linear system of equations? So now, if we start with the system AX equals B, multiply both sides on the left by P, we get PAX is equal to P times B. And now we can use the fact that if PA is equal to LU, and we use associativity, we now have the two systems LZ is equal to PB and UX is equal to Z. Okay? So that means that before we do the forward substitution with L, we have to apply the permutation matrix P onto the vector B. And that just means reordering the entries of B. So if we want to write it out as an algorithm, first we factor PA is equal to LU by doing Gaussian elimination with row pivoting. Second step, we solve LZ equals PB by forward substitution. And then finally we solve UX equals Z for X by factorization.